This is Andy Wilson and Adam Huckle's circuit diagram. It's a buck converter for our power electronics assignment. This is what we've created, built, designed as our prototype board, and this is what we're going to discuss now in this video.
So what we've done is we've used a STM Nucleo development board to control the driver which controls the MOSFET. We have used a potentiometer connected to the board so that we can vary the pulse width modulated output via the board. If you look at the screen, we have a value of 48% at the moment, but if we were to alter the potentiometer, we can see that we can vary the duty cycle from 0 right through to 100%. If we leave it at around 50%, what we can do is when we can connect the oscilloscope probe to the output, we can then view the output modulated signal on the oscilloscope. So once again, if I was to change the pulse width, we can see that it decreases down to 0 and once again increases through to 100%. So here we have the MOSFET driver. We are using a IR2104. We have some additional components required to drive the driver. These are classed as bootstrapped devices. There are 2 capacitors and a diode. If you look at the datasheet, you can see that there is an example circuit diagram, the 2 capacitors and the diode.
Okay, and back to the circuit diagram, just to point out the components used. This is the MOSFET in our circuit. MOSFET, diode, Schottky diode, inductor. We've just so happened to have the 100 millihenry connected in circuit, but we have used the 560, which can be seen in the report. It's disconnected at the moment. Capacitor, 1500 microfarads. Capacitor, motor, which is our load in this project. Right, the capacitor is added to the circuit to provide smoothing of the output on the drain of the MOSFET, which is a replication of the driver circuit, T1 of the pulse width modulation, which causes ripple on the voltage output. The issue with the capacitor is that on switch off it causes a huge current spike which can burn out the MOSFET. Therefore, the inductor is added to counter this, but the issue with the inductor is it adds a huge spike with turn on. Therefore, to counter this, the Schottky diode is added to dissipate any current around the circuit and away from the MOSFET switching.
So just to explain a little bit about the voltages that we've got going on within the circuit, we are powering the STM board via the USB from the laptop. This takes a 5 volt input but gives us a 3 volt output on our pulse width modulation. This can be seen on the oscilloscope. So the divisions we have here are 1 volt per division, so 1, 2, 3 for our 3 volts. We then have an external power supply connected in. This is giving us 18 volts. This can be seen by using the multimeter and connecting it across the connection points. So 1 point here, 1 point there, and you can see that we are reading 17.99 volts. We can now turn the circuit on using the on-off switch, and there goes the motor. So roughly we're at 50% duty cycle, so we'll be getting an average voltage output across the motor of around 9 volts. As we turn the potentiometer, we can see that the motor slows down and speeds up, which shows that the output voltage is changing. And back to the 50% duty cycle. I'm going to switch this off now, and thank you for watching our video.